Okay, this is test one of plasma deposition. See the electrode inside?
Notice how things are hugging the wall of that electrode like that. You see where that's going through there? I'm afraid if that was on metal, it would be
arcing.
Yes. I feel really comfortable doing it this way, Dave.
Okay, we have the clock set at 2 minutes, and then at 2 minutes, we're going to open up the door, and we're going to check the temperature, and if everything looks okay, we're going to go a little bit longer.
There's no interruption from starting it.
Yeah, I think it should start right up.
Yeah, it's a good machine.
So we have a microscope view of what the electrode coating looks like beforehand, and then we're going to check it afterhand and see if we see a change.
Can you imagine, even with the vent open, how quickly this pump pulled it down?
Right.
And we were waiting, but we never get up because of it. That's a good lesson, isn't it? Now once that's closed, the other ones are infinitesimal.
Yes.
Infinitesimal.
Yeah, look at how the pump is quiet now, and we're at
That gauge is
20 something inches of vacuum.
It doesn't mean nothing. It's just
Okay, so-
measuring a position on a dial.
Okay, get the temperature. I got the temperature gun.
You always open it up. Wait. That's right. It's a little warmer than body
Okay,
temperature.
let me check it.
90, 100.
Okay, the electrode seems to be
Is electrode
the aluminum.
cooler?
The aluminum is 70
Yeah.
degrees.
Big heat
The
sink.
ceramic block is 100,
There you go.
and the electrode is 95.
Isn't
So
that
it's-
interesting?
Yes, it's definitely,
The hottest thing in there is the ceramic block.
yep, the ceramic. I know. That's weird.
Well, here's a nice thing. It can take the temperature, but I'm amazed at that thing. You know what? It could have been that concentration. The aluminum rod is, if you look at the concentration of the plasma, how it was massaging the base of the rod.
Right.
You know, okay, we're gonna, I don't mind setting it up. What do you want to go for 4 minutes or 5?
5 minutes.
All right, fine. I'm confident that this is going to, we're not going to end up melting plastic here or anything like that.
Right.
Okay, so we have, ready?
Yep.
And what time? 5. Okay. Two seconds is going wrong. How's that? See how I know it?
Yeah, that's incredible.
Didn't I say 2 seconds and when I
Boom, boom, boom. Okay, so we have 5 minutes. Now, I'm going to give you a little bit of an update of why we're doing this. Okay, so what we
You
discussed.
like my shit here?
Yeah, we love your shit, that's for sure.
Yeah.
Okay, so this
Oh, is
this
that
invention is something that we'll show you the plans later, but it was designed by Arthur Devine. Okay, Dr. Devine. But the reason we're doing this is because the hydrogen metal that I developed, we're using this during the process. So I developed the process, Art developed the plasma microwave here. And so we're using it for this particular process related to the full spectrum plasma force gravity thruster, called the ripple, because it's going to be a ripple through space, that's for sure, pulling gravity. The reason we know this is because the hydrogen metal that I produce, it has some characteristics to it. There's a video that we'll load, we're going to unlock, and you're going to see the metal. The metal, even though it's magnetic, even though it's conductive, it's extremely strong. But it's not only just strong, it has a characteristic. You cannot detect it with a metal detector. Okay? So it's diamagnetic metal, which is extremely rare. Hydrogen, what we've come to the conclusion is that it's hydrogen that is what causes our gravity. Okay? You just have to bear with this subject for a moment. Stretching that understanding just a little bit further, we know hydrogen makes graphene. We believe, this is not a hypothesis, this is a potential belief, that in space, the fabric of space that's been elusive technically is graphene, just stretched a little bit bigger in the vacuum than we're normally used to, which is tying the fabric of space together with hydrogen. Now, the metal has another characteristic. When we tried to magnetize it and give it a high capacity DC discharge in the electromagnetic effect, basically how you make a magnet, putting it on a water scale, 1 ounce of material floated up and down the scale spectrum 4 grams each way for specifically an hour and 15 minutes roughly. That hour and 15 minutes relates exclusively to AU 197M, the single atomic state of gold. Okay? When the single atomic state of gold, AU 197M, falls down through its radioactive state, the half-life is 1 hour and 15 minutes exactly. These follow suit to hydrogen. Hydrogen is a switch. It's a very intense heterodyne switch. That's the proton inside of hydrogen. Now this is hypotheses based on observations. It's graphene is what a proton is. That's how we're only able to control the proton in proton spin technology and either attenuate it, put it through a lambda swing, which is just a fancy word for going from center left to center right. Right positive positive, negative negative, left negative negative, positive positive. That's a lambda swing. And that is the simplicity of how to control the proton. But you have to have the correct power. When you try to do it with electromagnetism, you swing the lambda to one side and that's it. You can never get a swing. So we have only a couple more seconds for the first run, and that is the metal that we're going to use through the thruster to pull gravity over sound, over speed. Okay, let's check the temperature.
Aluminum plate's body temperature.
Okay, the electrode is now 150 degrees.
Fahrenheit?
On the tip, 145 to 153. It's about even across. The ceramic is now cooler. The aluminum is much cooler. Okay? So let's go for another 5 minutes because we have part
Good
two.
Concept.
Yeah.
All right, what does it last?
We have to do this
It'll go five more minutes. It's gonna be too hot to touch, though.
Okay, let's find out.
So,
Now we're going to come in. We know there's a threshold of 143 to 150 degrees during all heat cycling. So we're going to, would be technically the second heat cycle. And we should, if we can't get any more temperature out of the electrode, then we're going to stop there. Okay. The reason we're doing this for the ripple, the gravity thruster, is because now we've come to the conclusion that sound goes the speed of light. Gravity waves, we know, go the speed of light, 186 miles per second. The fastest that we can go right now is 200,000 miles per hour with an ion thruster, which has no brunt. And it only has enough thrust to hold, to push the exact weight, as per NASA, of 10 quarters in your hand. That's all the thrust it has. We're talking about pulling, squeezing, and thrusting gravity 33 times the mass of gravity. Okay? If we can go 33 times the mass of gravity, we can take a calculation that's very simple. The next planet may be 4 to 6 light years away. That may have light. It has light. It has all the spectrums: blue, the yellows, the reds, the greens. The planet is 2 times bigger than Earth. It has 32 hours rotation. It's closer to the sun, but their sun is smaller. It has a mean temperature of 78 degrees as per NASA. So if we can go the speed of light, we can all be very patient on a 4-year trip to get us there. That's pretty fast. Now, when we get close, all we have to do is turn around the ripple and thrust and push off gravity with a specific fuel that I've produced. It's called Pure E, and it's a superconductive fuel. That fuel has enough potential, we could basically push off the sun. Bounce off the sun, take a soil sample, and come back without being burned. That's how powerful this fuel is, called Pure E. Now, and there's samples of that on my website, on the YouTube, okay? It's lighter than the vial that it's held in, but it's been built on these same principles, using vacuum, using linear magnetism, using gravity imposed over materials to make them heavy or light, okay? Because we can understand amplifying gravity finally. Well, now take that 4 years, divide that into 160 or 1,600 and something days. Now times 33. That gets us to the planet in 44 days. That's a return path of, let's just say, 90 days. And we can go, okay, there's something there, or there's nothing not. The ion thrusters right now, they're using a ridiculous amount of energy, 44,000 watts. You guys have been seeing over the videos through the bow tie of superconductivity. Oh yeah, I'll give you 44,000 watts through the bow tie of superconductivity, but I'm only using 60 watts in. That's energy conservation, all the way up and down. Using that power supply, inducing on the spacecraft. We'll use this as an example because we only have 1 minute left. Now on the plane of the craft, pretend that thruster right there, that electrode is the ripple, the engine. I'm an engine builder. I understand thermodynamics in engines. So that engine is in the middle of the craft. Now we can go straight, and if we adjust the lambda, the craft won't rock, but the lambda will. So anywhere on the craft, you're going to stand on gravity. Anywhere. if gravity is 4 dimensions over 6, now you have this dimension. So anywhere on the craft, you'll be able to walk basically on the inside of that dome or the outside, and you won't know the difference. The same as being on the northern and southern hemisphere of the planet. Now let's check the temperature.
Okay, Patrick came to take a peek.
Okay, let's check the temperature and see where we're at.
We may reach an equilibrium.
Not quite. The temperature of the electrode is now 170 degrees. Okay, 178 degrees. The ceramic is 154 degrees, and the aluminum is 100 degrees, and then 80 degrees on the outside. So let's go for another 5 minutes.
Aluminum hasn't gone up a bit.
Nope.
Right?
Nope.
See? That's a
We're
good
still
sign.
safe.
Very, very safe.
But the electrode's taking the juice.
That's right. But still, it's no hotter than what you might cook any food with.
I think we're safe for another 5 minutes.
Oh, we're safe for 10 more minutes.
Okay, let's do 10 minutes.
Oh,
Because I've got 10 minutes of talking to do.
how about 7 minutes then?
Okay, 7 minutes. Well, then let's just do this. Do the number. 7,
No, press start.
time. We're going to do 7, 4, 2, 3. Because that, oh no, that's way too much.
Just
Clear. We're going to do 7, 4, 2.
That's it.
But there's a 3 on the end of that because that's the actual ohms. 0.00742 3 ohms of what our superconductive circuit is actually at.
Well, 7.5 minutes would be 7:30.
Yep. Okay.
Okay, so
Boom.
you could say we're 7.5 minutes, right? Approximately 7.5 minutes.
Right. Okay, so back to the gravity of the craft. Because we can adjust the lambda, okay? I'm going to show you something. Would you just hold the phone so that they can see that? Will I be right back? Okay, so that just hold on to the phone. Don't let go. Hold on to the phone. Hold on to it. But don't get your fingers in front of the camera. Okay, good enough. So what we showed NASA in 2007 is that we can impose a gravitational field on any metal. And so we just touched a piece of stainless steel to the potential in 1 second. And the stainless steel, before we did that, we rolled the stainless steel on a granite block, and it rolled right across the granite block. Then we touched the potential right onto the stainless steel. Then the stainless steel flopped and only magnetized to Earth. Okay? They were impressed. Now we know that we can induce the magnetic field, the gravitational field, on any metal. So this is just a quick representation. Okay, so if you can hold the phone just like that. Okay, get your finger out of the way. Okay. All right. So now we're on the craft. And what I'm saying about swinging the lambda, we can swing the power. Okay? Like this. If we go 8.4 in either direction, swing the lambda of the circuit, that will give us the same wobble that the Earth has. Just like that. That'll give us the same wobble that the Earth has, but you'll never feel it. We're just moving the potential. So anywhere you stand on the craft, you are going to feel the same specific gravity that you feel on Earth, because all the metals are made on Earth, the gravity is made on Earth, and the only part of the of the thrust that and you won't even know it. So hold this right here for one more second. Okay, here's a preview of what we're talking about. This is the propulsion center of what I understand is the Z-pinch in science. But the blue is, we can now change the potential of the energy coming through. So as the plasma enters this cathode, it's going to be, the sound is going to be correctly ordered in a laminar flow. This particular muffler idea and understanding comes from Dr. Arthur Devine. But we just took it a little bit further, and now we have a Z-pinch, and what's inside of here is another flow. We're using the backside of a Tesla check valve, okay, to correct the flow and keep everything in one direction. This Z-pinch is the up, the blue Z-pinch is the down. As you can see, I've ordered the cups from big to small, across the Z-pinch, then small to big. Okay, it's specifically shunting the Z-pinch on this side for a reason. We'll explain that when this particular model is done. And that's the representation of the exhaust, but there's some green in there as well. You'll see in the last thing. This is just a model to show you what we're talking about. Okay. You'll never feel this. Even though this can be amplified up to 33%, 33 times gravity, you'll never feel it because everything will be encapsulated in this device, in this thruster. This is the heart of the thruster, and there's a lot of empirical data to support this in the portfolios of proton spin technology. Okay? Now we have 2 minutes to show you one more thing. I'm going to set that down. Grab the phone. Be careful so you don't push any buttons. Okay, so what we're showing you is circuit. Water, gas, electricity, and now sound all go in the same speed. So what I'm showing you is copyright of a circuit. The patent is already being applied for, so don't worry about that. This is what I want to show you. This is our understanding of coming through the bow tie of superconductivity in these shapes. Even though they look like a standard light bulb, it gives us the most powerful thrust through the superconductive circuit, where you would defeat this with electromagnetism. And all you need to know is that angle right there. Do you see how the magnets are not in the center? For a reason. We're taking 66 is our degree. That is our patent disclosure under a 66 ellipsis. Okay? This is not David LaPont. This is magnitudes more thrust than David LaPont. We've already tested it. You're going to see this in the model later on, shortly. Now we have 5 more seconds, and this will be the last heat cycling. Let's check the temperature.
doesn't it?
Yeah. Be fine. Everything will be fine.
Oh, it's hot. I wouldn't touch it now.
Okay. Now the electrode is 186, 190. It hasn't gone up any higher. The ceramic is 184, and the aluminum is still. It's actually cooler. Oh, it's 86. Right.
Ooh.
It's fine. Okay, so we're not going to get any more. This heat cycling, we're not going to get any more. We have to do it again after this completely cools down, so we're not going to touch a thing. We're just going to leave it like this, and we'll pick this up next time. Thank you for watching. This has been Ripple.